Okay, now crossing over to the determination of the function on the basis of what we have for a given Laplace transform. Now f of t is going to be the inverse Laplace of f of s. And here we have f of s is equal to s to the negative 3 halves is equal to the reciprocal of s to the 3 halves. And looking at what we have for f of t, okay, so we're looking at the inverse Laplace transform of the reciprocal of s to the 3 halves, and just kind of referencing what we have from the table itself. Now again, you have your function t of a, and you had the transform to be gamma of a plus 1 all over s to the a plus 1. And if you notice, okay, for the inverse Laplace transform of 1 over s to the 3 halves, and just to give you a little bit of a segue on this one, okay, so for 1 over s to the 3 halves, okay, so what I'm going to be looking at in this particular regard, okay, is that we're looking at the inverse Laplace transform. And say if I put s to the 3 halves in terms of s to the a plus 1, where you're looking at the inverse Laplace transform of the reciprocal of s raised to the 1/2 plus 1 degree. So this is going to signal that a is equal to 1/2. And so for what we're going to have in the mix, and looking at partitioning, okay, so you got your 1 over s to the 1/2 plus 1. Okay, but if I want to smooth things on out, so over s to the 1/2 plus 1, okay, from the transform, we're looking at the gamma of 1/2 plus 1. And guess what? 1 over s of 1/2 plus 1, that'd be like 1 over gamma of the quantity of 1/2 plus 1. And here we have a multiple. And just maintaining the color coordinating just to kind of show you where we're going. Say 1 over gamma of 3 halves. And we have times the inverse Laplace transform again, we have a gamma of 1/2 plus 1 all over s to the 1/2 plus 1. And a couple of things here. Okay, if you notice, for gamma of 3 halves, that is going to be the square root of pi over 2. So right now I have 1 all over the square root of pi over 2. And for the inverse Laplace, what I have here for gamma of 1/2 plus 1 all over s to the 1/2 plus 1, well, guess what? Your function is going to be t to the a. Well, with a at 1/2, well, the inverse Laplace transform of this portion is going to end up at t to the 1/2. And just looking at consolidating, so 1 over the square root of pi over 2, so I'm just going to take the reciprocal. So I have 2 over the square root of pi. We say we have times t to the 1/2, or by then we say we have times the square root of t, and you can consolidate, saying we have 2 times the square root of t all over pi. Okay, for the next Laplace transform, we have f of s is equal to the consolidated ratio whereupon we have 3s plus 1 all over s squared plus 4. And to get to the functions, okay, I'm going to separate the 3s apart from the 1, where I'm going to have 3s over s squared plus 4, and we have plus 1 over s squared plus 4. Now for the sum of squares, okay, now the corresponding functions, we're going to have the sine of kt and the cosine of kt. And if you notice, okay, we have 3s over s squared plus 4, so we have the variable s present in the second transform, and that's going to correspond to the cosine function. And letting what we have, first of all, letting first things be first. Okay, so we have so you have s over s squared plus k squared, and to get this in terms of what we have in the corresponding transform, so we can treat 3 as a multiple. So we can say we have 3 times the inverse Laplace transform of s all over s squared plus 4. Then we can say we have plus the inverse Laplace transform of 1 over s squared plus 4. Okay, so for what we have inside the first inverse Laplace notation, so you have a direct correspondence to s over s squared plus k squared. And to spell out what we have for k, it's strongly implicit. I'm just going to mention this. So 4 is going to be the square of 2. So we have s over s squared plus 2 squared. And for the other portion, so we got 1 over s squared plus 4. And if 4 represents the square of k and k is positive, well, k is going to be at 2. So for what we're going to have ultimately, okay, is that 1 over s squared plus 4. That is going to be 1/2 of 2 all over s squared plus 2 squared. And for what we're going to have in the follow through, okay, so we have 3 s over s squared plus 2 squared. Well, that is going to be the cosine of 2t, and by then we can move the 1/2 to the outside, and by then just take the inverse Laplace transform of 2 all over s squared plus k squared. So you have your k value at 2, and so that is going to be the sine of kt. Okay, so we have 1/2 of the sine of 2t, and that is going to be the final result. Okay, for the next Laplace transform, okay, we have 9 plus s all over 4 minus s squared. And for 4 minus s squared, okay, now you're going to have a difference of squares, which will factor out to 2 plus s and 2 minus s. And to make things Laplace transform friendly, okay, well, first of all, with partial fraction decomposition, okay, and this is from Calculus 2, if you were to perform partial fraction decomposition, well, your a value will be at 7/4 and your b value will be 11/4. So we will have 7/4 of the reciprocal of 2 plus s, followed by positive 11/4 of the reciprocal of 2 minus s. And for the first order binomials that we have in s, okay, we have, again, referencing the transform of s minus a, and this will correspond to the function where we have in terms of the natural logarithmic exponential base. And now, so if I rearrange the variable s out at the front, so 2 plus s, s plus 2, the same thing. So we have 7/4 of the reciprocal of s plus 2. And for the reciprocal of 2 minus s, that is going to be the opposite sign of s minus 2. So I'm changing over from positive 11/4 to negative. And for what we have in the case of the inverse Laplace transform, so I'm going to have f of t is equal to 7/4 of the inverse Laplace transform of 1 over s plus 2. We have minus 11/4 of the inverse Laplace transform of 1 over s minus 2. And if you notice, okay, we have with 1 over s plus 2, okay, this will be 1 over s minus negative 2. So for what I'm going to have in terms of f of t, so you got 7/4 of the inverse Laplace transform of s minus negative 2. So a is at negative 2, and your corresponding function part will be e to the negative 2t. And we have the inverse Laplace transform of 1 over s minus 2, where this time a is going to be at 2. So we're going to have altogether 7/4 of e to the negative 2t minus 11/4 of e to the positive 2t. And that'll be the final result. Okay, for the remaining item, okay, we have the Laplace transform given as 2 times the reciprocal of s times e to the negative 3s. And out of the transforms, okay, the closest match we have with e to the negative as over s. So reformatting what I have here, I'm going to keep the e to the negative 3s in the numerator. Once I convert to a fraction, and s to the negative 1 is going to be the reciprocal of s. Thus I have 2 times e to the negative 3s over s. So we have getting to the function. Now again, the inverse Laplace transform of e to the negative as over s is going to revert to the function which we have at u times the quantity of t minus a. Now for the Laplace transform, if I match up the format in terms of e to the negative as over s, okay, now we have the constant 2, which is a multiple. Okay, so if I move this out to the front, so I can say that I have 2 times the inverse Laplace transform of e to the negative 3s all over s. And guess what? We're going to have, you have e to the negative as is e to the negative 3s, and we have all over s. And with the constant 2 at the front, the result is going to be 2 times u times the quantity of t minus a, which in this case is going to be t minus 3. And that will be the result in this last function.